Actually, that's not what I want. What I want is the z value of the first model and the z value of the second model, I think. I'm not sure why these are y and not z. Let me just go back to my original and make sure that they're labeled correctly. So this is the x, this is the y, this is the z. Okay. So if I want to see what's in the brain, then I've got to have the z values. So I'm going to get rid of that. Okay. Where is it? I'm going to compare the two z values, the z value from the first set and the z value from the second set. Okay. Now I'm going to run this for 72 units of time, which is 72 hours. So that's 3 days. So you'll see what happens here is that in my first system, I start out with 5 units in the muscle and it keeps going down. What's in the muscle then gets into the blood and then goes over into the brain. And in the second system, there's nothing in the muscle, so what's in the blood comes from the drip and that goes into the brain. If I compare the morphine in the brain in the first model compared to the second model, you'll see that in the first model, because of the initial injection, there is a pulse that goes into the brain and then levels off. You'll see that in the second model, because of the drip, there's a slower build-up in the brain, but as the drip continues, it stabilizes in the brain. So this work set is about playing around with this, and you can put it in I mode, and you can play around with this. You can look at different injection rates. You can compare different strategies. So the fact that you've got two different models, and you can compare two different strategies means that if you're a medical doctor and you wanted to say, I want to get a certain amount into the brain as quickly as possible, but I want it to level off at a particular value, so what combination of drip and injection should I use? Then you can play around with this to say, okay, let's see what I can do. What would be a good strategy? Okay, so the model that you got for work set 5 is to play around with this and get a feel for what is the difference in having the extra reservoir of muscle where you put some morphine into the muscle and then it goes to the blood in the brain compared to putting an individual on a drip, compared to maybe a patient comes in. If you want to get a quick amount to the brain, then you can inject into a muscle if you don't want to inject directly into a vein. And then you can put the patient on a morphine drip and you can see how much is actually going to be in the brain over time. So if you're a pharmacologist and you want to understand how the morphine is going to the brain by giving intramuscular versus drip, then you use a model like this to play around with different doses. Okay, so that's basically the work set 5. But the work set 5 only comes after work set 4, which only comes after next week, which is your midterm. So your midterm is next Thursday. Work set 3 is due work set 4 the Thursday after that, and work set 5 the Thursday after that. So this work set is due 3 weeks from today. Yeah? No, I think you must. Yeah, I think you need to understand conceptually just the linear model in one dimension. So I'm giving you a preview of 3 dimensions here because one dimension is really not that interesting from an ANOVA and simulation point of view. But once you know what's going on in one dimension, then you can get a better feel for how it works in 3 dimensions. Yeah. Yeah. So if it's only, so if you have a look here, this is biflow because x, this could be positive or it could be negative depending if x is bigger than y. So you should always have it on biflow. Unless uniflow says that if it goes to 0, it switches to 0. It's kind of an extra condition on the equation. If I don't have that condition written on the right-hand side, then it should always be biflow. But there's some situations where you don't expect it to go negative. And if it does go negative, maybe there's a problem with your model. Your model should be preventing it from going negative. And in all of this, when I run this model, I think I've closed it now, you're using the Runge-Kutta method for integration. And you're using a delta t of 0.1. If something goes negative when it shouldn't, it may be that you have to use a smaller delta t because there's numerical errors in the integration method that is allowing it to jump over 0 and become negative. And that shouldn't really happen. Okay. So I'll see you on Tuesday then. And there will be a lecture on Tuesday when we talk about phase lines, equilibrium, and the hawk-dove game. And then, but the material on Tuesday is not for the midterm on Thursday. Yeah. Only the genetics ones. So there are 2 genetics ones, 40 and 41. I can't remember exactly which section. But I do recommend that you look at some of these examples of that I talked about today, where you integrate just these equations where we explicitly did an integration. Maybe worth looking at that. Yeah. Yeah. So I'm not going to give you complicated math. It's more how to model. It's all about how do you model this and what does the model mean and writing down the model. But more than that, you need to know how do you find an equilibrium of an equation and how do you talk about the stability. But it's not about giving you a complicated expression and saying find the equilibrium on the right-hand side if it's complicated. If I make you do anything, it'll always be simple. There won't be any complicated algebra. There'll be no sine functions. There'll be no quartic or cubic equations to solve. Okay.